Okay, so today I am covering mathematical variation, which is basically types of word problems, but they're usually worded very specifically and different from like other word problems that we've looked at. And a lot of these are either end up being like looking like a polynomial, but it's like one term. So you'll have something, a variable with some exponent, or it might look like a rational function where you are dividing by some variable, or it may be some combination of both. So there is definitely a question on this on the week 7 quiz and on the final exam, where you're going to have to basically translate some sentence into a mathematical equation. And that's really what mathematical variation is it's talking about how things change, and you're doing translations. So mathematical variation is a broad term applied to situations where you have multiple variables changing in multiple ways. So some may be increasing with an exponent, maybe some are dividing. You usually have more than one variable in these types of situations, but you could have one variable and or usually have, I guess, one input and then one output, but sometimes you could have multiple inputs and then one output. And a mathematical variation, they're generally still considered functions. So you could have multiple inputs, but as long as there's only one output, it's still a function. So we have 4 categories that we place variation in. There is direct, inverse, which sometimes people use the term indirect as kind of indicating the opposite of direct. There's joint, and then there's combined. So we're going to talk about these 4 different categories. So direct basically says as one thing is changing, the other thing is also changing proportionally. And essentially what we mean that there's a, there's like a ratio in how these change. Direct means they're both going in the same way. So if one variable is increasing, the other variable is also increasing. Or as one variable decreases, the other variable is also decreasing. So they are kind of going in the same direction. So lines are an example of direct variation, because as you go from left to right, as your x increases, the y increases. So lines are one form of direct variation. Joint is when you've got 2 things that are changing. Basically, that's when you have 2 specific inputs, and it's direct variation, but with 2 inputs instead of 1. So you'll have an x and a y and then a z. So you can't really graph these types of things unless you do like a 3D graph, but you basically have 2 inputs and 1 output, and everything is changing in the same way. Like the 2 are increasing, then the output increases with them. Inverse variation, which is sometimes called indirect, is when they're going in the opposite direction. So as one increases, the other thing actually decreases. And again, lines can be inverse, but this might be, you might kind of look like it's going down. As your x increases, your y is decreasing. So lines can be either direct or inverse when you're thinking about as terms of things are decreasing. Inverse, we usually look more in terms of dividing by variables to indicate that something is decreasing. Excuse me. So like a direct variation might be something that kind of curves as it goes up, and an inverse might curve as it goes down. So they're not always just lines, they're usually curves. And so that just is explaining like what happens to the variables. One increases, the other decreases. And then we've got combined variation, where you've got, again, more than one input and one output, but the 2 inputs are doing opposite things. So one is increasing, the other is decreasing, and then the output is doing something. So, or they're kind of they're both going one direction, the other one's kind of going opposite. It's kind of hard to explain. I wouldn't worry so much about conceptually what these mean. I would worry more about how you write the equations for these, because the wording is very messy, so to speak, because it can describe multiple types of graphs. You know, if one increases, the other one decreases, or, you know, things like that. There's lots of graphs that could fit into that category. So we have very specific ways that we translate these variations. So direct variation, we translate as a linear equation, essentially. So we have some unknown value k that we use, which is a constant of variation. And when it's a linear like this, it's basically equivalent to the slope. And so the wording that translates into an equation like this is y varies directly as x, and y is directly proportional to x. When you're translating it, the very first variable that you see in the sentence is the thing that you're setting it equal to. So y is first, so it's going to be y equals. Then you see the word directly, and you basically say, okay, that means I need to have my constant of variation k, and then I'm multiplying it by what comes next. So when you see that word directly, think about its multiplication by what follows. So joint variation is basically the same thing, but you've got more than one variable. And again, you're going to consider it as you're multiplying. So in this case, we have two variables that are inputs, w and x. So you see y varies jointly as w and x. So again, the first thing is y, so it's going to be y equals. And you have another phrasing, y is jointly proportional. And that word is, when we do math translations, is always equal. So you see, you have these and you think y equals. Then the word jointly is going to tell us we are multiplying what follows. So again, that is going to be multiplication, but you've got two things that you're multiplying. You've got both variables that are being multiplied together. And then you always have that k in your function. Inverse variation is basically the opposite. We're dividing instead of multiplying. So you again have y varies inversely, or y is, and those are translating as y equals. And then that word inversely is going to indicate you're dividing by what follows. And the k, that constant that we always have in here, is always going to be present, and it's always on top. So you're not going to divide by k. So it's just going to become the top of your fraction here. But when you see that word inversely, it's going to say, okay, I divide by what follows that. And then combined variation is where you're doing both. You're multiplying and dividing. And so when you've got the word directly, that means you're multiplying. So if we have y varies directly as w, you're multiplying by w. And then it says inversely as y. So you're dividing, or that's supposed to be x, not y. Inversely as x. So you're dividing by x. So you're looking for these words directly, inversely, to indicate whether you're multiplying or dividing. And then the variable that follows it is what you do with it, what is getting multiplied, what is being divided. So it's really doing a translation and knowing what these particular words mean. And anywhere I see the word varies, that's where I put my equal sign and then my value k, because you're always going to have a k in these. So those are the most basic forms, but we could have exponents on these. We could have radicals, have square roots. And so you'll see some additional wording, like it might vary directly as the square of x, which means that it's going to be x squared. Or it might say the square root of x. So then you need to have a square root of your x. So these are, you're really paying attention to the words, and it's like we're going back to week 1 where we had all of the math, the terms, product, all that kind of stuff, that translation. You're using that again when you get to variation. So there's a basic procedure for when you're doing problems with this and you're doing actual word problems that you're trying to solve. So the first step is to always take the words and translate it into your equation. And just remember, you always need to have that K in there. So that's the first thing that you do. And generally, when we write these variation models, there's no numbers at all. It's only variables when we first start. They'll give you numbers, and you use those to plug it in so you can find out what K is. So you can actually solve for that constant and find out what that constant is actually equal to. So once you find out what K actually is, then you're going to write the equation again, but now you have a number instead of K. And that's your finished model. And then if there's actually something past that where they want you to actually answer a particular question using that model, using that equation, you go and do that. So there's 4 basic steps for variation, and you may be asked to do any one of these 4. So if you're asked to give the variation model and they're giving you numbers, you have to go through steps 1 through 3. If they don't give you any numbers in the problem, you only need to do step 1. If they're giving you an actual question to answer, you have to go through all 4 steps. But so you have to kind of go in this process, but where you stop kind of depends on what the question is actually asking for. So here it says practice translating the sentences into variation models. So I'm focusing on the translating part into the equation, because once you have the equation, most people are able to then do something with it afterwards. You got to plug in numbers that you're solving, that kind of thing. The hardest part is always writing the equation. So we have the average cost per minute, C bar, that's how we read it out loud, for a flat rate cell phone plan. I got several typos here. Plan is inversely proportional to the number of minutes used, N. So there's a lot of words here, but we're going to kind of distill it down to the most important things. So our variable C bar, and then we've got the word is, which is an equal. So I'm going to have C bar equals. Because it's always going to go in order as you read the sentence. You're writing the equation in the order that you read the sentence. So we've got our variable C bar, and then we've got the word is. Then we've got inversely proportional, which means that we are dividing, which we do as a fraction. And when I fill that in, the top of the fraction is going to be our constant K. So you just kind of translate inversely proportional as K over something. And then we are proportional to the value N. So that is what goes in the denominator. So you're pulling out the actual variables that they're giving you and ignoring most of the words themselves. And you're looking for keywords is, which gives us our equal sign. The word proportional, or whether we've got inversely, directly, joint, one of those things tells you you're going to have your K, and then kind of what the actual thing you're going to do is whether you're multiplying or dividing. And then what follows that, you're looking for your next variable, which was N here. So you end up with your model. And a model is the same as an equation. It's just we use that term when it's sentences. when it's like a real world problem. So we've got C bar equals K over N. And we can't actually do anything with this model unless we're given numbers so that we can start solving, but that's fine. That's not what we need to do here. We're just practicing the translating part and getting the equation from the sentence. So are there any questions on that first one? Okay. Second one, we've got the volume V. So again, as soon as that you see that first variable, so that's going to be V, I'm going to write that down. Volume V of a right circular cylinder varies. So if you see the word varies instead of an is, that still means you're going to have your equal to. And then jointly is going to say that we're multiplying. So I'm going to have my K, and then everything that follows is going to be multiplied by whatever the variables are. Make sure that I don't cover the J there. So jointly is everything's getting multiplied. So we've got our next variable H. So I'm multiplying it by H of the cylinder, and then you go and you look for your next variable, and as the square of the radius R. So I've got my next variable R. But we do have to kind of read the sentence. It says the square of the radius. So that word square is telling us that we are having an exponent of 2. We are squaring. And so while for the most part, we're ignoring most of the words and just looking for the variable, you have to look for other words that are mathy, like square, square root, cube, that kind of thing, because those are part of the equation that you're writing. So we've got V equals K, because we just always have that constant in there. And that jointly meant multiply. So as the height H, so we're multiplying by H, and then square of the radius R. So that's multiplying by R squared. And then that gives you your model that then you can, if you had some numbers, you can plug them in and, find some answers. Are there questions on this one? How do you know where and when to plug in K? So K always goes after the equal sign. And if it's multiplied, it's going to be the first thing that you see. And if you've got a fraction, it's going to be the top of the fraction. So you're always going to have a K in your equation. And it's either going to be just in front of all the things that are multiplied or on top of the fraction part. There are other questions. Okay. So translating again here, we've got the variable E is directly proportional to S and inversely proportional to the square root of N. So we've got the variable E, so I'm going to have E. We've got the word is, which translates as an equal sign. And you're always going to have K in here, so you can just kind of put your K after you do the equal sign, just so you don't forget it. We've got directly proportional, so that says that everything is being multiplied, so it's going to be K in front, and then what follows is going to be multiplied. So it's directly proportional to S, so it's going to be multiplied by S. And then we've got this word inversely proportional, which tells that we're dividing. So now I'm going to write a fraction. I'm going to create a fraction. So everything that I had before the words inversely proportional, essentially is the top of the fraction. And then the square root of n. So I need to have the square root symbol in the bottom of the fraction, because whatever follows the words inversely is on the bottom, and then n is inside that square root. So we have E equals KS over the square root of n. So directly proportional is multiply, inversely proportional is divide, and it creates a fraction. So this is an example of combined variation, where you've got a direct going on and an inversely going on. So you've got both happening at the same time. So let's take a look at the second one here. We've got the variable d varies jointly as u and v, and inversely as the cube root of t. So d, and then when you've got the word varies, that's going to be your equal sign. So I'm going to put my equal sign, and then I'm going to put my k, because I'm always going to have a k. Jointly means there's going to be more than one multiplication. So if it's jointly as u and v, the u and v are both being multiplied together. So that's going to be u and v following the k. And then inversely, so that's where we're dividing. So I'm dividing by what follows. So I'm going to create a fraction. And then we've got cubed root of t. So the root, it's a cubed root. So I need to make sure I put that symbol. And then t is what's inside there. So we have d varies, which gives an equal sign. And I'm going to have that k. Jointly means what follows are being multiplied together. So u and v are being multiplied together, and they're being multiplied with the k. Then we've got inversely, which is the fraction you're dividing, and then you're dividing by the cubed root of t. So you write your cubed root symbol, and then t goes inside there. Any questions? Okay. Now I'm going to throw in some with some numbers so we can kind of, now that we've done some of the writing the models, you're going to see how a full problem works out here. So the number of people that a ham can serve varies directly as the weight of the ham. An 8-pound ham feeds 20 people. And we've got two questions here. How many people will an 18-pound, man, my typos are just all over the place, pound ham serve? And then if a ham feeds 30 people, what is the weight of the ham? So first step is to write the model, and we're not given variables in this case, so we need to determine the variables ourselves. So we've got the number of people that a ham can serve before the word varies. So one of our unknowns is number of people. So usually for number of people, I will use n. So I'm going to just say n is number of people. And then it says varies directly is the weight of the ham. So that's the other known we have, is the weight of the ham. And if you look at our numbers that they give us number of people and weight of ham. So I'll use W for the weight of the ham. And it's always good to write your variables down and what they represent, so that way you know where you're plugging your numbers, what number goes where. So once I've determined what my variables are, I can start with my translating. So we've got the number of people n. Varies, so the word varies is going to be our equal sign, and I'm going to put in my k for my constant. Directly, so that says we're going to be multiplying by the weight of the ham. That's what follows. So this is going to be n equals kw, because w is the weight of the ham. So you can basically turn number of people into n, and then your varies directly, and then weight of ham you can turn into w, and you replace those with your variables. So that's step one, is just getting that model. Step two is to try to find k, and you find k using usually the second sentence that they give you. They'll give you some relationship. They'll tell you how many people, how much, in this case, the 8-pound ham feeds this many people, so that we can use this information to find out what k is. Because that second sentence is giving us that n is 20 and w is equal to 8. So I'm going to plug that in. So you have 20 equals k times 8. You want to make sure you put them in the right places. And then you solve for k. So we need to divide both sides by 8 in order to solve for k. And this will give us what's called the constant of variation. So you'll grab your calculator. And usually for variation problems, because they're word problems, we do use decimals instead of fractions. So I have 2.5 equals k. So it's not often that we use fractions in our variation problems. So I can just do the division. So now that I know what k is, I can rewrite my equation with the value that k is equal to. So now I have n is equal to 2.5 w, because now we've solved for k. Once you've done that, now you can actually answer the questions that they give you. So the first question is, how many people will an 18-pound ham serve? So our weight is equal to 18, and we're looking for what n is. So I'm going to use my formula. N is equal to 2.5 times 18. Whoops, I accidentally hit the division button. So you multiply and you get 45. So n is the number of people. So it will feed 45 people. So an 18-pound ham serves 45 people. And then we have a second question here. If a ham feeds 30 people, so n is equal to 30, what is the weight? So now we're plugging in a number for n and solving for w. So n is 30. So 30 equals 2.5 w, because now we don't know what w is. So I need to divide both sides by 2.5. And that comes out to 12. So to feed 30 people, you need a 12-pound ham. So this is the process that you have with variation problems. Generally, the first sentence is going to give you the model. The second sentence gives you the information you need to find k. And then the third sentence will be the actual question you're trying to answer. And then if there's another question after that, a fourth sentence, then that will be another question that you're trying to answer. And they're usually all set up this way. We're, in that format. And so you're just working like sentence by sentence by sentence when you're doing a variation problem. Are there questions on this problem? Okay. So here's another one. The distance that a bicycle travels in 1 minute varies directly as the number of revolutions per minute that the wheels are turning. So this sentence is giving us the model. A bicycle with a 14-inch radius travels approximately 440 feet in 1 minute if the wheels turn at 60 RPM. That second sentence is giving us the information to find K. And then the third sentence here is actually a question. How far will the bicycle travel in 1 minute if the wheels turn at 87 RPM? So the 1 minute part is not a number we are ever going to be using in our equation because it's just part of the variable. Because notice we're not asking about different amounts of time. It's always asking about 1 minute. So that's constant. And so that's not actually going to be a variable. Because there's at no point in this example is time different from 1 minute. So it's constant. So it's not going to be used. So we'll start by defining our variables. So we have the distance that a bicycle travels. Maybe I'll highlight, oops, I meant the highlighter. So the distance that a bicycle travels in 1 minute, that is basically our first variable. And you don't have to write that whole thing, but we can just write that it is the distance and just say, D for distance, but it's basically, that's what we're going to represent by the distance a bicycle travels is going to be D. And so when I'm translating this, I've got D equals, because I've got the word varies. So I'm going to try to color code this one and see if it helps. So the distance the bicycle travels in 1 minute. And then we've got the word varies. And when I see varies, that means, okay, that's where I'm going to have my equal sign. And I usually just plop the K down at the same time. And then I've got the word directly. So that means I'm going to be multiplying. So if you want to help you remind yourself that, you can put like a little multiplication symbol there. Just say, okay, I'm going to be multiplying. And then we've got that it varies directly as the number of revolutions per minute that the wheels are turning. That is basically our next variable here. So maybe we just call that R for revolutions per minute. So that's going to be after our equal sign. So you can try to color code. I know my orange and my yellow are very similar here. And then color code so you can see what translates as what into your equation here. So we've got D equals KR. So that's the first sentence. That is our model that we write. Second sentence, a bike with a 14-inch radius travels approximately 440 feet in 1 minute if the wheels turn at 60 RPM. So notice they give us 14-inch radius, but that's not one of our unknowns. That first sentence didn't say anything about the radius of the bike. So we don't need that. That's just an extra piece of information that is not necessary for a model because it was not part of that first sentence. So we can just ignore the 14-inch radius. And we have our distance, which is 440 feet. And then they're giving us the RPM, which is 60 RPM. So we're going to plug those numbers in. So I'm going to just kind of color code. So we have, oops. We had, Keep picking the wrong color. So our equation is D equals KR. And our distance is 440. And then the RPM is 60. So it's going to be 440 equals K times 60. So now we need to solve for K. So I need to divide both sides by 60 in order to solve this problem. So 440 divided by 60. And so this is actually going to give us a decimal. It's 7.33 repeating. So I'm just going to kind of round to 2 decimal places. And that equals K. So a problem in ALEKS, they would tell you what to round to. They would say like round to 2 decimal places for your value for K. If it doesn't specify and it is a repeating decimal, then you might want to leave it as a fraction, which my calculator, I can convert between fractions and decimals. And so in fraction form, this is 22 over 3. So you kind of like, if you're doing this in ALEKS, you want to find, look, does it give me a amount to round to? And if it doesn't, then stick with the fraction version. But if it does say like rounded to decimal places or something like that, you can use the decimal version. We're going to use the decimal version though, because that is usually it's real life. We're working with decimals, not fractions like that. So we found K. So now I can actually write my equation again, which is D equals 7.33R. I found K, I can replace R, and then I have my D and or I can replace K, and then I have my D and my R. So now we go to the final sentence here. How far will the bicycle travel in 1 minute? So we're looking for how far. So that's asking about the distance. And they are giving us the RPM if the wheels turn at 87 RPM. So they're giving us the value for R. So I've got D equals 7.33, and then R is 87, because that is our value for the RPM. And so you just need to multiply those, 7.33 times 87. And so because I rounded to 2 decimal places, my answer ends up having 2 decimal places. I get 637.71. Now, if you use 22 over 3, you actually come out to 638. So just as a side note, because it does affect your rounding, if you use 22 over 3 and then multiplied by 87, that gives you a whole number, 638, which our rounded number with the 2 decimals would round up to that. So again, you want to pay attention to the rounding. Sometimes it says don't round any intermediate steps, so you only round at the end. So you really need to pay attention to the wording there to know where you're rounding, how far are you rounding. Like they might tell you to round to the nearest whole number, which then you'll get the same answer no matter method, whichever method that you do here. But you do want to basically include your units in your answer. So if we round to a whole number, we would say that it is 638. And then the units for distance are feet, because that was the units for the 440. So if you're not sure what units there are, go back and look at what units you used when you plugged in to find K. And so distance to find K was in feet. So your answer is going to be in units for feet for distance. Third questions. Okay, so this is my last example. We've got the stopping distance of a car is directly proportional to the square of the speed of the car. So that's our first sentence. That's what you're going to be using to create the model. Then we've got if a car traveling 50 miles per hour has a stopping distance of 170 feet, find the stopping distance of a car that is traveling 70 miles per hour. So this is a second sentence, but it is combining two steps. The part before the comma is telling you what you need to find K, and then the part after the comma is telling you what you're actually solving. So that comma is kind of dividing it into two separate pieces. So it's combining it into two separate steps. And then we have another question to answer after that. If it takes 244.8 feet for a car to stop, how fast was it traveling before the brakes were applied? So we'll start with the first sentence here, and I'll do the highlighting thing again. We've got the stopping distance of a car. So that is the first unknown or the variable that we have. So that is D. I'm going to use D for stopping distance. So D. And then we've got the word is. So is always translates to an equal sign. So I'm going to just put my equal sign there. And then we have directly proportional. So that word directly means we're multiplying. So directly proportional, and we're always going to have K. So usually when I have an is kind of deal, I put K with the directly proportional. So I'll do K and then my multiply to remind myself that I'm multiplying because it's directly. And then it is directly proportional to the square of the speed of the car. So speed of the car is our other unknown. So we can call that S. I'm actually going to use R because for rate, so that my S doesn't look like a 5. And then the one thing that we haven't translated here yet is the fact that it says it is directly proportional to the square of the speed of the car. So that means that there's an exponent on this. So it's going to be R squared. So the stopping distance of a car is directly proportional to the square of the speed of the car. Gives us D equals K R squared. So now we're going to move on and we're going to stop at that comma for the next sentence because that's what we need to find K. So we've got a car traveling 50 miles per hour. So that's going to be my distance. And it has a stopping distance or has a stopping distance of, oops, I've got the wrong thing colored. I'm like, wait a minute. The stopping distance of the car is in blue. So that's going to be 170 feet. Has a stopping distance of 170 feet. And then the speed of the car comes first. So be careful when you're translating these that you notice that it gave us the information in the opposite order of how it was originally worded. So our previous example, it kind of gave us in the same order that it was worded. This one, it was in opposite order. So this is why I write down, and I try to color code too, but kind of write down to make sure that I'm using the right numbers in the right spots. So stopping distance, I initially was like, okay, I'm going to highlight it in the same order, but it's like, wait, no, that's speed. That's not stopping distance. So just, be very careful because they can word them in different orders. So we've got stopping distance being 170 and then the speed being 50 miles per hour. So when I plug this into my formula, I've got the stopping distance, 170, and then equals K. And then it's going to be R squared, and R is the speed. So that's going to be 50 squared. So we have 170 equals K times 50 squared. And we're solving for K. So we first need to square 50. So 170 equals K times, and I believe that's 2,500. Yes, 2,500. And we're solving for K here, so I need to divide both sides by 2,500. And so that gives us 0.068 equals K. And then if you want, you can write that as a fraction, which if you do that on a calculator gives you 17 over 250. So you can do it either way. It didn't have a repeating decimal. This actually comes out to a terminating decimal. So we won't have any rounding issues here. But since we do have a decimal in that second bullet point, it makes sense to have like a decimal in our equation here. So we found K, 0.068. So we now need to do the part after the comma. It says find the stopping distance of a car that is going 70 miles per hour. So now they're giving us another R, 70 miles per hour, and we are finding D. So we are finding the stopping distance. So I have my equation, which is D equals 0.068 R squared when you actually plug in your value for K. And now we're looking for D. So we're going to plug in the value they gave us for the speed. Oops. Which is 70 miles per hour. And then you're going to do that math. So we have to do the exponent first for the order of operations. So that should give me 4,900. Yep. So it's 0.068 times 4,900. And so then I multiply that. We get 333.2. And the units are feet because our stopping distance numbers have all been in feet. So the stopping distance of a car that's going 70 miles per hour is 332.2 feet. So that we finally answered the first bullet point. And now we go to the next bullet point. If it takes 244.8 feet, so now they're giving us another stopping distance for a car to stop, how fast was it traveling? So now they're looking for the speed of the car. So now we're going to take the same equation, but now we actually have a value for D and we're looking for R. So D is 244.8 feet and equals 0.068 R squared. We're solving for R. We're solving for the speed. So I'm going to first divide both sides by that decimal. So I need to divide by 0.068. And that actually comes out to a whole number, 3,600. And that equals R squared. And we want R, not R squared. So we need to take the square root of both sides. And normally when we're solving quadratics with square roots, we get two answers, a positive and a negative version. But since we're solving for speed, negative speed doesn't make sense. So we're only going to use the positive version. We don't have to worry about the plus or minus because a negative does not make sense in this context. So when you take the square root, you get for R 60. So we get 60 equals R. So that means the car was traveling 60 miles per hour. So it's always good after you've gone through this is just to keep going back to the problem and making sure you've actually answered what was asked and you've done everything, that you haven't missed anything, you've got your numbers all in the right place, because it is like a multi-step kind of thing, but you're like working sentence by sentence by sentence. You got this, you do this, then this, and then you just, it's kind of very methodical, if that makes sense. Are there any questions? Okay, so that's variation. So like I said at the beginning, you're going to have one question on this on the quiz and one question on this on the final exam. And I would recommend for your notes, having these, whether you have flashcards or you just have a page, putting what it kind of translates to, what the words translate into, so that way you can do the translations, maybe having an example of what it would look like. So like putting these in your notes and then making sure that you have, if I can get to it, the steps for solving so that you go step by step by step. So that is all I have.